Soumya Jyoti sir, you there?
Hello? Yes.
Yeah.
Yeah.
Yeah, okay, sir. So we are waiting for some more participants to join. We'll be starting from 5 more minutes.
Okay, no problem.
Okay, sir.
I'm here, no problem.
Okay.
Okay.
Soumya Jyoti sir, you there?
Yes, I'm here. Yeah.
Okay, okay. So we are starting the session, sir.
Okay, no problem.
So, good evening to all. I, on behalf of Department of Physics, Tripura University, welcome you to the fourth evening of the AICTE Training and Learning Academy Faculty Development Program on Fundamentals of Thin Film Preparation and Characterization Techniques. In this evening, our speaker will be Dr. Soumya Jyoti Ray, Department of Physics, IIT Patna. The title of his talk will be Surface and Interface Characterization of Thin Films. Dr. Ray is working as an assistant professor at IIT Patna right now. He has completed his master's from IIT Kanpur and PhD from University of St. Andrews, UK. His main research interest lies in experimental and theoretical condensed matter physics, specifically 2D materials, nanoelectronics, spintronics, resistive switching, topological insulators, quantum metrology, etc. Dr. Ray was awarded with some prestigious awards like DST Early Career Research Award, DST Inspire Faculty Award, EPSRC Doctoral Fellowship UK, Academic Excellence Award, Indian Academy of Science Fellowship, etc. Dr. Ray is also the member of German Physical Society Germany and Institute of Physics UK. He has published more than 40 research articles in internationally peer-reviewed journals. He is also awarded with projects funded by DST and UGC-DAE. With this note, I welcome you, Dr. Ray. Please kindly deliver your speech.
Thank you for the nice introduction, and thanks to the organizers for organizing this event. So I'll share my screen, and let me see. I hope my screen is. Hold on. Yeah, I think my screen is visible, right? Yes. Okay. Yep. Okay. Okay. So okay, is my PPT visible?
Yes, sir. Yes.
Yes. Okay. So first of all, thanks to the participants also for their time. I understand this is almost the end of the day, and I mean, you might be tired already. So I'll try to be as gentle as possible so that things are a little bit bearable for all of us. So the title or let's say theme of today's presentation is surface and interface characterization of thin films. And as we know that thin films can be characterized in various different ways, and the surface quality and the interface quality is very much important, let's say, for any kind of further development of thin film based technology or any devices that we make, because most of the structures in thin film geometry that have more than one layer, so typically like 3 layers, 5 layers or something. And since these layers are quite thin, so typically any interface inhomogeneity or any kind of impurity or disturbance that is present at the interface, it can actually create a lot of disruption in the performance. So it could be conduction, it could be in the, let's say, optical properties, it could be in the transport behavior, magnetic behavior. So depending on like what sort of applications we are looking for, whether it is electronic, optical, or let's say spintronic, so these interfaces play a major role. However, there are not that many techniques available which can directly probe the interfaces. Okay, so here we will try to see what are the available techniques and what do they do and what are the limitations and what we can do, etc. So let's see. So first let us try to understand, so what is a thin film. So as we know, most of the materials that we see in our day-to-day life, they are three-dimensional. So here, for example, you can see that this is like a block of, let's say, some certain material X. So this is three-dimensional. Now if I use some vapor deposition technique, then I can try to deposit a small or thin layer of this particular material on a given substrate, and then I'll end up with a thin film of this particular material on top of this substrate. So what changes here in this process is that there is an effective change of dimensionality, because the source material is three-dimensional in nature. However, when we are depositing it as a thin film, then the system is becoming effectively a two-dimensional system. So I'll not call it as a completely two-dimensional, but you can say like it is close to two-dimensional system. Now, if we are having such a change in the dimensionality, so as a result, let's say if we are thinking about, let's say, quantum mechanical terms, then the electronic behavior will change because the confinement will be different, and also the amount of surface area of the material will be increased compared to the bulk form. So if we are talking about, let's say, surface to volume ratio, that will be enhanced in the thin film geometry compared to its three-dimensional structure. So as a result, what happens is that since there will be more number of atoms which will be available on the surface, so these atoms can be prone to any external excitation. So this could be like any electromagnetic excitation, or it could be some chemical species, so anything. So that kind of opens up a lot of application possibilities, for example, like in sensor, or even like plasmonic applications, etc. Now, in typical thin film devices, you will have not one layer, but let's say more than one layer. So here I have kind of made this structure. So here this is layer L1, and then you probably start with another material, then you get another layer L2, and that way you will make a heterostructure of maybe few layers, and that entire structure is meant to behave or perform certain operations. So that is a thin film heterostructure based device, or let's say thin film heterostructure simply. Factor of the, let's say, properties of this particular structure. So here you can look at this length scale diagram. So if the thickness is about 1 millimeter, which is roughly like 1000 micrometer, then we'll call it as a sheet or plate like structure. And if we keep reducing this number, and if we are going somewhere close to, let's say, 1 micrometer, so between 1 to 100 micrometer, this region is the region of thick film. And if we are below this number, and let's say it could be as low as up to few angstrom, like 10 angstrom, then we are calling it as a thin film. So these are like typically atomic layers, which are maybe one atomic layer or few atomic layers, which are kind of only getting deposited onto a particular substrate. So that's how basically you can think of like how the dimensionality changes with change in the thickness here. So that way the behavior or the performance will also get affected. Now, typically, the two most common deposition process techniques which are used for thin film growth, they are called as physical vapor deposition, or PVD, or chemical vapor deposition, that is, let's say, CVD in that sense. So now, in the case of physical vapor deposition technique, what happens is that you will have more or less like a dry setup. So you will have a source material, and typically that is a pure material. Like the purity will be quite high, typically like 99.9 or 99.999%, something like that. And then you try to create a controlled atmosphere, and under that atmosphere, one tries to kind of grow the material in different techniques. So like electron beam deposition, then thermal deposition, or DC or RF sputtering, etc. So I'll kind of like discuss a little bit on these things in the next slide. And in the case of chemical vapor deposition, what happens is that there will be some reaction which will be taking place. So it's basically like some chemicals will be used. So one will work as a precursor, so that will initiate the process, and you will have like a large size or let's say some moderate size substrate on which you can grow a particular layered material. So I mean, both these processes have their own advantages and disadvantages. For example, in terms of purity, cost effectiveness, and then kind of like industrial scalability, etc. However, both of them are being used extensively both in industry and also in academia. Okay, so now let us try to see that how can we basically do the characterization. So here I will first start with how does the deposition technique works for let's say here I have taken two examples, and then subsequently I'll keep on explaining how does the characterization also comes into picture here. So let us first try to see here when we are talking about this first example, that is the electron beam deposition technique. So the way the deposition works is that you have a vacuum chamber. So this is most likely quite robust and like a let's say stainless steel made chamber, and then one has to kind of like pump out the gas from the chamber itself through some vacuum pumps, and you have to create a pressure of the order of, let's say, either 10 to the minus 6 or less millibar. So that way what happens is that you will have a very kind of like contamination free atmosphere here in the chamber. Now you have a source material which is three-dimensional in nature, and you put it inside a boat or something, and then here you will have an electron beam which is kind of like being created here through voltage acceleration. So you will have a like a 10 or 20 kilovolt power supply, and then this electron beam will be created and it will be focused so that it falls on the substrate. So it will create some localized heating, and then the atoms from this particular point will get energy from this beam, and they will be kind of moving away from here and they will move upwards. So here on top you can see that there is some sort of a substrate holder. So here you put the substrate, that is like, let's say, silicon. Typically you can put it here, and then so it is positioned in such a way that directly these atoms which will be coming out of this source, they will go and fall on top of this. So since the pressure is quite low, so here these atoms will have a very large mean free path. So which means that the chances of scattering will be less, which means that more or less whatever number of atoms are coming out, they're likely to go and fall on top of the substrate. So that way you will have a very kind of, let's say, controlled atomic deposition on top of the substrate. So here you can also have some freedoms like substrate rotation, and then you can use substrate heating also to kind of control the growth process. For example, sometimes that helps to get a better quality film. Now, so let's say this is the process in which, so this is a very basic way of thin film deposition. Now, let's say in this particular step, if we want to monitor the quality of thin film, or like whatever is being deposited, then what can you do here? So in this particular type of system, the only thing that can be monitored, let's say commonly, that is the thickness of the film. So let's say if I grow, or let's say run this process for 30 minutes, then I'll get a particular thickness, or let's say if I run it for 10 minutes, then I'll get a particular thickness, etc. So I can get an approximate thickness through this thickness monitor. So that is the only thing I can get here. Now remember, this is an in situ characterization process. So it means that here the characterization is being done as the sample is being grown. So we are not kind of exposing the sample to the atmosphere or any other condition as such. So it is kind of going to give us a more detailed insight of whatever characterization we can do at this stage. So but however, here we don't get much information. So the only thing we can get is the thickness, that is whatever is the amount of material that is deposited here. Now if we simply switch this thing to a slightly advanced version of this thin film deposition, which is called as, let's say, molecular beam epitaxy. So here what happens is that the deposition process slightly differs, but the basic mechanism stays the same. So here also you will have a slightly bigger chamber, and the pressure has to be much smaller here. So typically like 10 to the power minus 11 or 12 millibar. And in order to do so, you have to use more powerful pumps. So let's say once that is established, Then here you will have the substrate. So that substrate is again fitted with a similar kind of attachment. So there will be a rotation that is possible here, and then some heating, etc., or let's say some particle movement if one wants to lower it down or kind of, let's say, pull it slightly up. That is possible. Now here the materials that is going to be deposited, they will be kept in these cells. So they are called as effusion cells. So here these materials are again very high pure materials. For example, let's say if I have gallium or phosphorus or nitrogen, anything, whatever I want to deposit, so here that particular element will be stored, and that is very high purity. And here the each of these cells can be heated individually. So what do I mean by that is that, like, here as you can see that the electron beam is hitting let's say the entire source material in one shot. But here basically the heating will be more controlled and kind of like, let's say, much more slower in that sense. So as a result, whatever so there will be some coils which will be running around these cells, and that heating will be used to kind of create an atomic beam of this particular material, which will be kind of leaving from here, and they will appear on the sample surface. Now here, as you can see, there are few other arrangements which are kept here. So there is this cell shutters. So it means that, let's say, if I want to deposit a particular cell, particular material, then I'll open that particular shutter, or if I want to close one, that I can do. Of course, these are like mechanical assemblies. And another thing here which is important is that this main chamber, that is the deposition chamber, it never actually gets exposed to atmosphere. Okay, so that is something which is not possible here. So what do I mean by that? So let's say if I want to grow a thin film on a particular substrate, then what I have to do is that I have to load the substrate which is outside the chamber, right? So somehow I have to open the chamber, and then let's say in the case of electron beam deposition, I have to open the chamber somehow and I have to load it here. Now once I do it, then even for 5 minutes, 10 minutes, that particular chamber, it gets exposed to atmosphere. So whatever are the kind of like constituents that are there, so there might be some dust which is present in the atmosphere, or some other contaminants, they can appear here. And although we are pumping it down, but still it is possible that some of them will stick to the walls or somewhere, and it will be hard to take them out. Okay, but in order to get rid of this thing here, in the case of this MB deposition system, what happens is that there will be a secondary chamber where through which this transfer happens. So this secondary chamber will be connected to this main chamber, and there will be some valve which will kind of work as a door. So here, let's say in this secondary chamber, so here actually you can see like there is this airlock valve. So there will be secondary chamber. So here the substrate will be transferred, and then you will kind of like pump it down, and once you feel that like you have reached the desired level of pressure, I mean that has to be comparable, of course, on both sides of the valve, then you open it and then you transfer the substrate here, and then after this transfer is done, you again take the rod back and then you close the valve. So in essence, basically this chamber never gets exposed to air. So that way kind of you can maintain a very good purity in this particular system. Okay. So now here, of course, let's say if you want to grow some compound or let's say element, then what you will do is that either you are kind of firing up one of the cells or maybe more than one cell, and that will kind of go and react on the substrate, etc. Now, since this is an atomic deposition, so it's like a very controlled layer by layer deposition. So here there is an in situ characterization tool which is available. So that is called as this RED, or the full form is reflection high energy electron diffraction. So what it does is that here basically you will have an electron gun, and that gun is kept in such a position that basically this electron beam which will be accelerated from here or released from here, they will come and they will kind of fall on top of this substrate. Okay, now once that is done, then this electron beam will be kind of diffracted, or after interaction they will come back from here, and there will be a detection screen which will detect that. So what happens is that, let's say if there is a deposition going on, then this beam is constantly falling on top of this. Of course not like for the entire period, because then substrate will burn probably, but you keep on kind of like checking it from time to time. And as you have, like, let's say one layer of material that is deposited, then you will get a change in the pattern of this reads on the read screen. And then let's say if you have another layer of material that gets deposited, then the pattern will change. So you can actually monitor the growth on a real time basis, or let's say a layer by layer basis. And here you can get a lot of information from this particular measurement, that whether the system that is being grown, or let's say the thin film that is being deposited here, whether it is epitaxial, whether it is single crystalline or polycrystalline, and whether, like, let's say some new like the growth conditions are changing, or like let's say the crystalline quality is changing during the course of the deposition. So those things actually you can monitor through this read pattern. So let us see how does it look like. So here you can actually see that there are a couple of few plots, or let's say read patterns that have been shown here. So let's say when we have only two layers, then you will see some of these bright spots, and there are some like weakly visible lines here. And then when you have more atoms that are deposited, then you can see these lines are becoming a little bit more brighter, but they are now becoming, there are like more dots that are present here in these lines. And then once you have more and more number of atoms that are coming up, then you can see like this pattern is also changing or evolving. So this is like a 0 nanometer, then 4, 30, 40. So with change in thickness, you can actually measure these patterns, and that way you can actually get quite a lot of useful information. For example, let's say here on the right hand side, you can see there are two particular types of read patterns have been shown. So here you can see these streaky lines, and they are quite bright. And within each of like two consecutive bright lines, there's basically a dark spot. So this kind of structure corresponds to an epitaxial growth. However, if we look at this bottom part, so here we don't see such bright lines. Rather, we see that there are this kind of like this semicircular lines. So they typically correspond to a polycrystalline structure. So here we have a higher degree of crystallinity. So that is why so epitaxial means that like the structure at the bottom and the structure on top, they are having a similar kind of, let's say, crystallography, and also the lattice spacings are also similar, which means that there is negligible interfacial strain, or means that like like one unit is falling on top of each other exactly at the same position. So that way basically you will get like higher reflect, or kind of like this refracted intensity, and that is why you are getting these sharp bright lines. But here, since it's polycrystalline, so the degree of crystallinity is low, so that is why you will get an average intensity, but there are basically only kind of few lines which will be appearing here. So that way you can actually monitor these things, and from here you can also kind of try to estimate the lattice spacing of the structure here also. So this is again an in situ deposition characterization technique of the thin film, or if one wants, then one can also use it to monitor the interface quality, or let's say how the interface quality is being changed. Okay, so now I'll just briefly talk about how does the chemical process of thin film deposition work. So there are two main techniques. I'm not saying these are the only two, but they are most popular, let's say. So one is spin coating. So here what happens is that you will have a substrate, and that is kind of being fixed to some, let's say, chuck or holder. And so this is vacuum sealed, so that it doesn't move much. And then you will have some material which you want to deposit. So typically it could be an organic material, it could be a polymer. So these are some materials which are difficult to grow, let's say, in physical vapor deposition process. So you take that material into a solution form, so you dissolve it into some solvent, and then after that what you do is that you kind of like drop a particular volume of that material onto the substrate, and once it is done, then basically you start rotating the substrate at a desired rotational speed, so typically like few thousand rpm. And since there will be centrifugal force, so the layer which is kind of put here, that will be kind of growing, or let's say it will be all over the substrate, so that way you can get a more or less uniform film on this particular substrate here. So once that is done, since it is in liquid form, you have to dry it out. So you try to dry it out so that the solvent goes out. And once that is done, then basically your film is almost ready. If you want, you can heat it up also again. Or other than that, you can try to grow the next film or next layer, whatever you want. So this is a quite easy, or like let's say straightforward process, because you don't need very high level of vacuum, etc. So of course there will be some compromise in the quality, but there are some materials for which the spin coating is the only options. Okay, then there is chemical vapor deposition. So this is also a very popular technique, specifically with the rise of graphene and other of these 2D materials. So here what happens is that you will have like a, let's say, cylindrical chamber, and so this is like a part of a furnace, you can say. So there will be heating, and so there will be heating zone, and then there will be precursor gas which will be passing, and the substrate will be there. So on top of the substrate there will be some reaction which will take place, and this gas flow will kind of take away the remaining constituents. Okay, so that way you can get a more or less uniform layer of thin film. So for example, I mean, industrially this is used quite a lot. So here the advantage is that you can get a thin film of very large area without having quite a lot of expenditure. So these are the two main techniques in chemical vapor deposition. Of course, there are like atomic layer deposition is also there, which is very much useful these days, but this is a little bit expensive. Okay, so far we talked about in situ characterization and how they can be done. Now there are quite a lot of ex situ characterization, which means that when we take out the sample from the chamber, then we are already exposing it to the atmosphere. Then what we can talk about this. So there are several techniques at this stage. So for example, there is X-ray diffraction. Then there is X-ray reflectivity. So they will give us information about crystal structure, then thickness, density, surface and interface quality, etc. Then there is X-ray photoelectron spectroscopy and also some optical measurements. So they can give us information about the chemical composition and the presence of defects and some optical properties, etc. Then we have electron microscopy. So there are two main parts here. One is scanning electron microscopy, which is mostly a surface sensitive technique, and then transmission electron microscopy. So this will give us kind of structure and chemistry of the sample. And then there is atomic force microscopy, which will give us information about the surface morphology at a very atomic scale. And there is an additional technique which is called as neutron reflectivity. So I'll talk a little bit about this so that like we'll get a feeling about how does this thing work. So this also kind of is quite useful technique, and this is something which can give us information about this buried interfaces and some magnetic behavior also it can actually probe. So let us try to see how does these things come out. So let's say first we will talk about X-ray diffraction and X-ray reflectivity. So we all are more or less familiar with this technique, I believe. So here typically we have, let's say if we imagine that this is a more or less crystallographically oriented thin film, then there will be this like a periodic array of these layers, and then you will have an incident beam of X-ray. So typically this is copper K alpha, or let's say molybdenum K alpha beam. So more or less low energy, and that incident beam of X-ray will come up and kind of like it will, let's say this is the incident beam, it will interact and then it will get diffracted. So this is Bragg's law. Theta is the incident angle, and then 2 theta is the diffraction angle, and with reference to the scattering vector, we can actually measure this thing, and the scattered intensity, or let's say the diffracted intensity, will measure, and you get a diffraction pattern. Now, for thin films, actually, there are a couple of factors which plays here. So one is this theta, of course, that is kind of out of plane kind of variation, what it gives. And then there is this phi, which can give us information about the in plane variation. Okay. So for example, let's say if I keep the beam at a particular position of the sample, and then if I only vary theta, then I'll kind of get the variation with respect to only let's say this diffraction angle. However, if I keep the value of theta fixed, and if I change phi, then I can get an in plane variation of what happens here. And if we want to measure the off specular thing, so they are basically specular detection, which means that like whatever is the angle here, that is kind of like the same line, the diffracted beam we are detecting here. But there could be off specular diffractions. For example, if the surface is, let's say, liquid surface, or like let's say slightly inhomogeneous, then there could be like beams which will be diffracted from other angles also, not other angles, like in other directions. So if we can measure that also, so there are some experiments where people do that, then we can get a more or less detailed information of the overall texture of the surface. So that is kind of the, here it is called as the tilting angle. So that in some cases people can do, but it is not very much commonly used. Okay, so let us now try to see. So this is X-ray diffraction. So here you will typically get the crystal structure, or let's say the space group, or let's say whether like which crystal symmetry does it belong to, etc. Now, there is another very important factor for a thin film or heterostructure which we need to characterize, and we need this information very accurately. That is the thickness and the interface quality. So diffraction will not give us this information. So here what we need to do is that we need to do a reflectivity experiment, and we can do it with X-ray also. So what we have to do is that we have to keep this angle 2 theta very low. So typically below 10 degree, like 6 to 8 degree maximum you can go. So that way you can imagine that the beam is like coming almost very close to the sample surface. So it's kind of like a reflection that is happening. So here if you do that, then you have to kind of like measure it at very fine angles. And since, let's say, if we imagine that there are like more than one layers which have been deposited, then what will happen is that here the resulting reflectivity pattern, it will kind of show us these oscillations. So these oscillations will have a kind of, it could have a varied amplitude, and the periodicity depends on the film thickness. So here you can see like basically here there will be a certain angle that is called as a critical angle, so above which this kind of oscillations they start coming in. So this is mostly the substrate effect that is coming up. So this angle is determined by the substrate, and after that you will basically get this oscillations because of this thin film. So you can imagine that like this is a reciprocal space. So here if you have a thickness d1, then there will be some 2 pi over d1 that will give you these kinds of oscillations. So if you have a thick layer, that means your oscillations will be much faster, so the period will be much smaller here. However, if you have a thin film, then the periodicity will be slightly larger. So it can happen that like if you have more than one layer, one is very thin, and other one is very thick, so you can get like both the thicknesses, or let's say oscillations corresponding to both the layers, by having two different periods. So for example, this first oscillation will correspond to the thick layer, and the like a more slower oscillation will correspond to the thin layer. And here the sharpness of the oscillations, it is determined by the interface quality. For example, if the interface is very much kind of, let's say, uniform, then you will have more constructive interferences, and as a result the oscillations will be more sharp. But if the interface is very rough, then you can imagine that their output intensity will not be as good as that of a very smooth interface. So then you will kill these oscillations, and as a result you might get a very rough or average oscillations. So that kind of tells you a kind of detailed insight about the interface quality. Okay, and here overall this kind of profile it decays as uh, it's a 1 over, let's say, theta to the power 4 kind of dependence. What here you have, like the overall intensity I'm saying. So that's how it did kind of goes down. So from this particular kind of, let's say, experiment, X-ray reflectivity, you can get quite a lot of useful information. Okay, so now here I have actually taken a figure from a thesis. So here it shows how these two techniques together, or let's say in combination, can work and give us some very useful insight. So for example, here in this case, this is a titanium nitride thin film which has been grown on silicon 001 substrate. So here this is kind of like the Z oriented substrate, and this is the deposition condition, like in 760 degrees Celsius was the substrate temperature. So here in this first figure A, you can see this is like a 2 theta scan. So that is the diffraction, typical XRD diffraction. So here this is the substrate, silicon substrate peak, and here this is the titanium nitride peak that is kind of here. And then here on the right hand side in figure B, you can see B and C both are phi scan. So as I said, that this is like kind of, here you have, let's say, this particular peak that you know that you are going to get a kind of intensity peak at this particular angle. So what to do is that you fix the theta value at this particular angle, and then you do an in plane kind of variation. So here you are changing the phi, so you can see this is a complete 0 to 360 degree rotation, and here you get like 4 peaks. So this tells you that you are having a 4-fold symmetry here. And similarly, if we are like marking a different peak, then for example, this is a titanium nitride 111 peak, so this is probably not shown here. So then you will get another kind of diagram, like similar kind of pattern. And here also this 4-fold symmetry is kind of visible here. So that way you can also get this confirmation from here, like the crystal structure. And now here this is the X-ray reflectivity data. So here you can see basically there are quite a lot of oscillations that are coming up, and if you fit it, then you can get actually the informations like surface like sample thickness, roughness, etc. Okay. So now the next thing I will quickly talk about is this neutron reflectivity. So this is actually a kind of, let's say, complementary technique, or let's say something which works on the same direction as that of X-ray reflectivity. So here what happens is that instead of X-ray, we are using a polarized beam of neutrons. So as you can see that there is this incident vector and then these reflected and transmitted vectors. And typically if you have only one substrate, then you will get a pattern like this. So you can imagine like this is like 1 over q to the power 4, that kind of dependence. And if you, let's say, have a layer here, so then basically these neutrons will kind of experience a difference in the potential, and as a result what will happen is that the incident and transmission k will be different. So there will be some delta E, and that will kind of give you some basically oscillations here. So let us try to see. So this is transmitted, then this is the reflected ones. So here typically you will get a similar kind of pattern as that of the X-ray reflectivity. So and you can fit it. So here the question comes then, okay, so if I'm getting a similar kind of thing, then why do I need to do this thing? Because neutrons are, let's say, more expensive to get, and secondarily it is having, let's say, usually lesser intensity compared to the X-ray one. So why it is? So the reason is that here actually, in addition to this kind of simple reflectivity, or let's say the thickness and roughness, what you can get information also about the magnetic texture. So since neutrons are magnetic kind of in nature, so if there is a magnetic layer and they say there is a non-magnetic layer and there is another magnetic layer, so the magnetic environment across the depth will be different. So as a result, if the neutrons are polarized, that means there will be up and down neutrons. So then let's say they will experience a difference in the potential for the two types of neutrons. So for example, let's say if there is one bottom layer is non-magnetic, then there will be no difference in the potential that will be experienced by them. However, if there is a magnetic layer, then this red neutrons will have a slightly higher potential and the blue ones will have slightly lower. Let's say if the next layer is more magnetic, then the contrast will be even more, and so on. So as a result, what happens is that since the up and down spin neutrons will experience a different kind of magnetic or let's say overall potential, so that will be reflected in the final reflectivity. So here what you will get is that you will get a particular reflectivity pattern corresponding to the spin up states, and other one is the corresponding to spin down state. And from there you can estimate something called as the spin asymmetry. And if you do a little bit of like modeling, or let's say like the same thing you have to do for X-ray reflectivity also, then you can actually find out that how does the interfaces behave magnetically, and if there is any kind of like buried magnetic interfaces, etc. So here we'll look at a very simple example, that let's say here if you have a typical superconducting film, let's say this is a lead film which is grown on a substrate, and then there is a capping layer just to protect the system. So this film has a thickness like let's say 1000 angstrom, so between 1000 to 3000 angstrom, and here you are applying a magnetic field. Okay, so then what will happen is that if you apply a field, then as you know in a superconductor, if you are below the critical temperature, then here the material can be in a variety of magnetic states depending on the strength of the applied magnetic field. So let's say in this case also, if the field is low, then it will be in a Meissner kind of state, and if it is in a let's say slightly higher applied field, then you can actually be in a vortex state. So here vortexes will coming in. So here through the reflectivity pattern, I don't think I have the image here, so that will lead to bigger discussion anyway. So just very simply I'll just mention. So here if you measure this reflectivity pattern in this case and in this case, then you will see a clear difference, and from there it is possible to kind of find out what is the particular state, whether it is Meissner state or vortex state, and even it is vortex state, whether it is let's say one particular array of vortices or two or zigzag or something, like these things could be modeled, and they could be found out, like people have done these things. So these kind of detailed informations can be figured out from such reflectivity behavior also. Okay, so next we'll talk about the most, let's say, common and popular kind of characterization technique which people like, so this is the most sought out one, so that is electron microscopy. So what happens is that this, as the name suggests, that this is microscopy. So similar to let's say an optical microscope, here also it is the electron beam which will work as to illuminate the sample. So in the case of light microscope, what you do is that you use some particular light, and that will kind of do some interaction, so you'll get some picture, image, or some resulting pattern from which you can actually identify the information. Here that will be the electron beam, and here also the beam has to be kind of handled quite carefully. So you are basically imaging the specimen to gain more information. Now you can ask like, why electron then, why not light? I mean the idea is quite simple here. Since light has, let's say, the typical lights what we use for optical microscopes, they have a much lesser energy compared to the electron beam. So since the energy is quite high, which means that you are more likely to get more detailed or like depth information of the structure and the composition of the material. So here the steps are quite similar to what it follows in the case of an optical microscopy. So here also you will have a source, that is the stream of electrons. So typically this is an electron gun which you will be kind of guiding with some voltage, and this beam will be kind of let's say ejected from this gun, and they will be accelerated towards the specimen, which is your sample in that sense. And you have to have some sort of condenser or let's say focusing arrangement. So typically these are like magnetic lenses which are used, and once that focusing is done, then basically you get a very much collimated beam, and then you will kind of allow it to fall onto the sample surface, and then there will be some interaction which will be occurring between the material of your sample and the electron beam, and the resulting output, whatever like the interaction is doing, that will be detected. Okay, so all the interactional effects will be kind of counted by some detectors. So there will be different kinds of detectors, and they will be transformed into an image. So so that like we can get a more kind of let's say clearer view of this entire surface area of, let's say, particular part of the sample. So here let's say if we the most common one which is used here is for thin film is scanning electron microscopy. So what happens is that here you will have an electron gun, so that will produce very high speed electrons. So typically you can see this is kind of like a field emission tip, so this is very sharp tip, and which means that the beam will also kind of, it is actually depend, I mean it is governed by like the shape of this thing. And then you will have a series of lenses and sample stage, and there will be detectors which will be present at different angles. So let us see if we have a picture here. So here you can see this is like a electron gun, and then here this kind of some condenser arrangement is here. So that is kind of a big, so this beam here is quite broad. Okay, so here you have to somehow put this beam into some particular form. So that is why this condenser is used, and some focusing is done here. So then once it is done, then basically you will have this beam that is here, and here is your sample or specimen slab. So it is coming here, and then after the interaction there will be multiple types of electrons that are coming up. So there will be secondary electrons, then there will be X-ray that will be coming up, and you will detect and you will kind of analyze them to find out different information. So here the typical resolution that you find is 0.5 to 4 nanometers. So typically this is the spatial resolution. So this is very high compared to the light microscope. So you can see the difference. Now, in order to operate, so this system must be under vacuum. So this is like high vacuum you have to kind of create, so that like there will not be any additional scattering from the electrons by any atmospheric entity, because whatever collision is happening, that is giving you the information about the sample surface or substrate surface. And here the sample can absorb or reflect electrons. So let us see if I have an arrangement here. Okay, yeah. So now the most popular one of type of scanning electron microscope, what is used here is called as FESEM, or field emission scanning electron microscope. So what it does is that you actually, you know, like you have the filament, and then you have the beam, but then you, this beam is not very much confined. So here basically you can use something like a field emission source. So this is called as a cold cathode. So here this electron gun can provide a narrower probing beam with high energy, and that will improve the spatial resolution and also the sample charging. What is sample charging? Since the beam will come and kind of hit the sample, so there could be some localized heating or charging, electrostatic charging can happen. Okay. So the advantage is that this FESM, it produces clearer and less electrostatically distorted image with a good spatial resolution. Down to 1 nanometer, which is 3 to 6 times better than conventional STM. So here you can see like there is basically this tip is there, as I showed you, and then there is basically, this is the beam, and then there is a crossover, and then you are kind of trying to focus it down. So that is how the FESM is works, but the basic interaction principle stays the same. So let us try to see what type of interaction happens here. So let's say this is the electron beam or electron probe that is kind of coming up here, and then it interacts. So there will be different types of electrons. So the first thing is that there will be secondary electrons. So and then there will be I think Auger electrons and backscattered electrons, and then there will be X-ray emission, and they will have basically like each of these types of electrons, they will have information about different parts of the sample. For example, this Auger electrons, they will be sensitive to this much kind of like thickness, 10 to 30 angstrom. Then backscattered electrons can provide you information which is typically of the length scale of 1 to 2 micrometer. Okay, secondary electrons are also sensitive to very small length scales, so etc. So now let us see what are these different types of electrons. So the first is the secondary electron. So what happens is that you have an incident electron, and then they are kind of hitting your sample surface. So there will be some collisions. So you can imagine these electrons as some energy. So essentially this energy is being absorbed by the sample, and this sample itself gets excited, and then it releases another electron, or let's say more than one electron. Since this is a different electron which is released from the incident one, that is why it is called as the secondary electron. So the primary one is the incident one, and the one that is released by the sample is the secondary one. So typically they have very low energy, so less than like 50 electron volt, and this production is highly topography related. Now, the another type of electrons will be backscattered electrons. So what is this? So here, let's say you have these electron beams, there will be scattering. Now, a fraction of this beam can be scattered back to the surface itself. Okay, so like they will not produce secondary electrons, but rather what happens is that they will come. You can think of it like a reflection or diffraction kind of thing. So these electrons will come and they will take a different path. Okay, so they are backscattered electrons. So these production of these electrons will be directly proportional to the atomic number of the specimen, and they can be used to detect the contrast between the areas with different chemical compositions. So so these are two main types, and then there is a difference between the images that will be collected through them. So for example, here you can see there is the secondary electron image and there is a backscattered electron image. So both of these approaches have strengths and weaknesses. So for example, if it is from secondary electrons, then they will have a higher resolution and higher contrast because they depend on the primary beam. But if it is secondary electron, then they will not be that much sensitive to these kinds of informations. Okay, so they'll be more sensitive to the topography. So here, for example, you can see like this deep, more like shorter cells that is inside the structure, or the topographical information are more visible here. So this is like more elemental composition they are more sensitive to. Okay, so now there is also this X-ray which can be produced here. So what it is that, let's say if the electron is somehow absorbed in the sample itself, and then some inner or core cell, I mean, if that electron or incident electron comes up and then it knocks out some, let's say, core cell electron of the sample, then that will jump into another cell, and as a result, you will have some X-ray that will come out, right? So that X-ray you can measure, and that can give you a chemical information, like what is the element that is present in the sample. Okay, so that could be like a volumetric information. So like these are the three main types which are coming out from here. Now, if you want to do a sample preparation, so here there are a few things which you have to focus upon. So first thing is that the sample has to fit inside the sample chamber, so it cannot be of any arbitrary shape. Then it has to be vacuum compatible. Now, not all the samples are vacuum compatible. For example, if you just put like some random powder, then if you are if you are like pumping it down, then this will be all over the place. And the sample must be electrically conductive. Otherwise, there has to be a conducting layer which has to be deposited on top of that. So typically, people deposit gold as a coating layer. So this is mostly used for insulating samples like polymer samples, and that is kind of, it reduces the heating also, the sample heating, surface heating. Okay, so that is more or less the ACM part, and now so I'll show some image at the end. Now another useful technique is scanning probe microscopy. So here what we do is that you have something called as like scanning tip. So that tip kind of measures either the tunneling current, or it can also measure the roughness or the inhomogeneity on the surface. So if it is measuring the current, then it will be scanning tunneling microscope, and if it is measuring, let's say, the surface inhomogeneity or roughness, then we will call it as a atomic force microscopy. So For I mean, the operational principle is also slightly different. The STM that actually needs a metallic tip, and the surface which is measuring also have to be conducting. Otherwise, the tunneling current will not be flowing here. However, in the case of AFM, this interaction is more kind of van der Waals interaction between the tip and the surface. So, depending on the distance of separation, you will get different modes of operation. Okay, so let us see how does it work. So first we'll have a brief look at the STM. So here this is basically like the setup. So here you have the tip and you have the sample. So as I said that this both of them have to be metallic, and there is some piezoelectric scanner which is attached here, and there is quite a bit of electronics that is present here. Anyway, what it does is that this tip actually moves across the sample, and there will be some barrier between this tip and the sample. So that is kind of the tunneling barrier. And since both are metallic, so there will be some current that will be flowing. There's a tunneling current, and it is being measured by this. So that current will be amplified, and there will be comparator. So a whole bunch of electronics is present here, and you will kind of get the information from there about the sample. Now here the tunneling current will go as exponentially with thickness. So if the thickness is quite large, or let's say sorry, not thickness, but the distance between the tip and the sample. So if the distance is large, the current will be small. So that we know already from like basic quantum mechanics. And this current will be used to generate an image. So we have to kind of scan it in all possible directions. And here basically I mean, you can get quite a lot of useful information, but there are few limitations. For example, the lateral resolution here is not that much huge. Okay, and since this is only used for conducting samples, so insulating samples cannot be measured with it. So that is a limitation here. Now here actually you can see there are basically two kind of like different modes of operation. So one is a constant height mode, and or let's say constant distance mode, and the other one is a constant current mode. So in the case of constant height mode, what you have is that you have the tip that moves across a particular height, and this is the path of the tip. And in the case of constant current mode, so it kind of moves so that the current stays kind of fixed. So you can see like if one stays fixed, other will vary. So for example, of course, your sample will have some kind of texture here, and that will be either reflected in the path of the tip, or let's say in the current that you measure. So that's how this thing works. Now, here, of course, people have done quite a lot of useful experiments. For example, the surface science have been developed quite hugely after the discovery of STM, and one can do atomic manipulation. And here you can see, like, you can view the atoms also. So that is kind of like a big kind of achievement of this technique. So in real kind of like one-to-one measurement, you are viewing these atoms here. So that is a kind of like very powerful tool here. Now, when we are talking about AFM, then, or let's say atomic force microscopy, or so as that name suggests, that we are basically dealing with atomic force. So here we are mostly dealing with the topography. So whenever like you are using AFM, it actually is governed by the force that is being acted upon between the tip and the sample. So either the force could be an attractive force, or it could be a repulsive force, and depending on that, there will be certain deflections of the tip, and basically that deflection will be measured, and that will give us the information about the roughness, or the let's say height related vertical information. So here the most important part here is that the cantilever. So here you can see how does the cantilever looks like. So this is supposed to have very high flexibility, which means that any small change in the force should be detected by this. And this high flexibility, it actually exerts lower downward force on the sample, and that will kind of result in less distortion. Now, typically, since as I said, like they have to be very much sensitive, so the spring constant will be of the order of 0.1 Newton per meter and have a very high resonance frequency as a result of that. So typically these tips are very thin in size, as you can see, like 20 to 30 nanometers. So like few atoms are there only. Okay, so compared to the cantilever, this is very, very small. So you can see like this is the tip. Okay, and then this tip will run back and forth across the sample. So you can imagine like such a small entity is scanning across the sample, and that has to be handled very, very carefully. Otherwise, what you might end up is that you might end up in breaking the tip. Okay. So now what happens when you are scanning is that there will be basically this tip is attached to the cantilever, and this XYZ direction, that control is there. So there will be some piezoelectric scanner which will be attached. So you can see actually this is the cantilever, and then the sample is placed at the bottom, and then there will be some feedback controller which kind of measures the feedback and controls it, and there will be some data acquisition. So I'll explain it in the next slide. So here the typical range of XYZ is like this. Of course, it varies slightly from model to model, but you can like take it as a finger like a rough number. Now, whenever you are basically applying a voltage to the electrodes, then there could be some bending or stretching, and the sample could move as a result of that. So here you have to kind of position it accordingly. So now here is actually on image here. So or let's say some sort of like a cartoon that explains here. So here you can see that this is kind of the sample surface, this purple or pink one, and then you have the tip, say the cantilever here and the tip here. Now there will be a laser beam which will be kept here, and this laser beam is directed to the top of this part, and the reflected beam will be detected by a photodiode. Now, as the sample keeps, not the tip keeps moving, and since there will be like inhomogeneity on the surface, so this tip is kind of going to sense that inhomogeneity, and as a result, what happens is that either it will go down or it will go up. Okay, depending on where are we. So the beam position or the diffract this beam here, whatever is appearing on the screen, that position will also change. So that will tell us about the like the roughness or the inhomogeneity that is present on the surface. So here we are not directly measuring this, rather the deflection we are measuring. So that information will be transferred from the photodiode to the PC, and once you construct this, so here basically you also store the location information. So for example, if you take it like a 256 by 256 pixel size, so you take like each pixel as one particular entity, so you get some information, and then that you store in order to create a, let's say, AFM image, which you call it. So you can imagine that image is constructed, it is not something that you are directly measuring. So here, for example, you can get a slightly better view that let's say if this photodiode will have, basically there are different detectors or pixels, basically detectors, let's say. So now if the laser beam is hitting it here, and then the beam is kind of appearing here on a particular diode. However, if the tip is on a different part of the sample, the beam will not be appearing on that particular one, but on a different detector. Okay, so that information is kind of going to help you, like, okay, what is the particular location and particular, let's say, height dependent information. So what is the deflection that is happening here, that is giving you the depth information here. So here you can see basically either it is going up or it is going down, and that way basically it is kind of moving from the original position, either moving up or moving down. So that height information is being stored in this way. So now let us see what is the mode of operation. So there, in order to understand that, we have to kind of look at this particular curve. So this is a force versus distance curve, and you have probably seen this curve earlier. So this is this famous kind of Lennard zones potential, a similar kind of curve you get here. So the essential idea is that we have two components. So basically, this is the interaction force that is being acted upon between, let's say, the tip and the sample surface atom. So here, when the distance is basically between the tip and the surface is very close, then there will be a repulsive force. So that will give you this kind of this large edge. And then if they are kind of quite far away from each other, then this will be an attractive force between these two. Now, since there is an attractive component and there is a repulsive component and they are acting together, that means there will be an equilibrium position also. So typically in the case of Lennard-Jones potential, there will be like an 1 by r to the power 6 term and 1 over r to the power 12 term. So you can see like this term is quite sharp and this term is slightly much lesser slope compared to this. So here this is the equilibrium position, right? So now depending on what is the distance between your sample tip and the surface, so you will be having different modes of operation. For example, so this is also called as this Van der Waals potential energy curve. So here if you are let's say slightly what can I say, like let's say far away from the surface, so if the distance is large, then you can use something called as a non-contact mode. However, if the distance is quite short, then you can imagine the tip has to come close to the surface, so that will be contact mode. And if it is in between, then we call it as an intermittent mode. So there are three different modes of operation. So one is called as this contact mode. Then there is this tapping mode or intermittent contact mode. So and then the third one is the non-contact mode. So in the contact mode, so you measure basically the hard sphere repulsion force between the tip and the sample. Okay, and in the case of tapping mode, this is basically the I mean it will kind of tap and move. Okay, so that way basically your cantilever has to vibrate at a very high frequency. And in the case of non-contact mode, it will kind of derive the image from the measurement of the attractive force. So here the tip does not necessarily have to touch the sample. Okay, so now let us see the different modes here. So let's say if we are in the contact mode, so as you can see the tip is touching the surface. So here we are in the repulsive region of this Van der Waals curve. So here basically since the tip is attached to the cantilever, so the spring constant will be quite low here, and the force can be like of the order of like nanonewtons to micronewtons. Now the pros here is that you can do a fast scanning, and what is the negative side here, that it is not suitable for soft samples. For example, let's say if you have a liquid sample or let's say membrane, then you cannot use it. Okay, so then the next one is non-contact mode. So as we seen already, that this works in the attractive region of the Van der Waals curve. And here basically since it is kind of like not touching the sample, so here the tip has to oscillate. So and then basically that will have to close to its resonance frequency without touching the sample. So here the advantage is that it is suitable for soft sample as it is not touching, but the negative part is that the resolution can be little lower because you are slightly above or let's say far from the sample surface. Okay, then there is this tapping mode, which is the intermediate mode. So here the typical separation can be between half a nanometer to 2 nanometer. So here the contacts can tap the surface, and that can cause a change in the oscillation amplitude of the cantilever, and which will be in response to the sample topography. So here the tip vibrates at a very high frequency, and the amplitude could be of the order of 10 to 100 nanometers. Now here the advantage is that we can have very high resolution imaging for softer samples, but the scan speed could be lower. So these are the three main methods of operation, and basically depending on the type of samples and of course the time you have, what kind of resolution you are getting, you can choose the things. So let us now look at what are the advantages and disadvantages of AFM. So here advantage is that the sample preparation is not very much complicated, so it's quite easy. Like you more or less can scan any sample which is having a roughness typically, let's say, of the order of nanometer. Okay, of course micrometer it could be, but typically if it's lower it's better. And then you don't need to have a specific kind of vacuum environment as you need for a scanning electron microscope. And you can of course measure the biological samples or softer samples, and the height measurement can give you good height information. Now what are the disadvantages? So the disadvantage is that improper measurements can damage the tip or the sample. So this is a big problem with this thing. Specifically, if you kind of look at, then for all the measurements that we have explained so far, let's say X-ray, then neutrons, and then I think this electron, scanning electron microscopy. In all the cases, the sample never gets touched physically by another entity. So that way you can say these are like non-invasive techniques. So your sample is not directly getting scratched by another entity. Of course, you can say if the beam energy is quite high, then it might damage the sample, but that the probability is quite low. Okay, because this sample can discharge also. Anyway, but here, since you are physically touching the sample with the tip, so if there is slight imbalance, or if you are not very much kind of accurately doing the thing, then either you can damage the tip. That is a very expensive exercise because the tips are quite costly, and the alignment also will kind of has to do every time you're doing it. And of course, if your sample is very crucial, then you might not get another sample. So that way, basically, this is a risky business unless you are an expert user or you are being careful in these things. The second thing is that the magnification is less because, as I said, more than 100 or micrometer range you can kind of measuring here. And the vertical range is also quite limited because as you see the force versus distance curve, if we are at a very large distance, then basically it's almost going asymptotically. So you hear that kind of in that range, you will not get much of force between these two. So the resulting information will not also be very much high. Okay, so these are the major advantage and disadvantage. Okay, so now with that we are almost coming to the end of this. So here we have actually few images. So that are so the left side is the image which are taken from some ACM measurements, and on the right hand side we have some AFM images. So on the left hand side here you can see that let's say for example in figure A, here basically you have taken this measurement let's say on a larger area, let's say 5 micrometer or so, and then you can zoom it in, and then you can try to find out more and more detailed information. So here you can get the texture. For example, here you can see these small kind of structures which are appearing here if you zoom it in more and more. And if you're using a proper software, then what you can do is that you can try to identify the size, and then you can kind of get the size distribution, and that will kind of tell you what sort of length scale are present in your sample. For example, if it's a nanoparticle or something, then that will tell you quite a lot of good distribution of these things. And here also you can see for different kinds of samples how much detailed information you can get. So the idea is that this is a very much specially sensitive tool. So here you can actually kind of differentiate between different kind of microstructures. For example, if it's a sphere-like, or if it's a tube-like, or if it's a seat-like structure, that actually information you can get here. For example, let's say if it's a as I said, a particle, okay, then you can expect it will be slightly spherical in shape. Let's say if it's a nanotube, then you can imagine how the shape will be one-dimensional. If it's say 2D surface, like a graphene sheet or something, then you can get the seat-like structure, and from here you can also try to identify the size also. So there are quite a lot of useful information which you can find out from here, and you can see like if you zoom it in, then the different textures will come out. So not necessarily that all of these informations will be available or visible to you at a larger length scale, but if you zoom it in, then these things will come out, and further analysis can be done, of course, from here. So here I didn't talk about tunneling electron microscopy, but you can imagine this is basically, so here in SEM, this is the surface, whatever interaction is happening, and then in TEM, whatever is tunneling through, that beam will be of interest. So here that will also give quite useful information about the crystal structure, for example, atomic arrangements, etc. You can find out. Okay, so now on the right hand side, this is the AFM topography. So here actually they have measured this. I think after certain times of growth. So this is a reference sample, and after 1 minute of growth, 3 minutes, 5 minutes, here they wanted to observe like what sort of evolution is happening. So here you can see there are like these small kind of islands and kind of hill-like areas that are appearing here. So although we don't see these things with a optical microscope always, so here with the AFM you can see these things, and here you can see the vertical resolution is also quite good. So that way you can actually kind of identify the surface texture at different positions, or let's say at different stages. Okay, so that way we have basically looked at like quite a few of the experimental techniques which are mostly used for this thin film and let's say mostly interface characterizations. So although like they are quite well developed and exhaustive techniques, but in some cases we might have to use a combination of all of them. So it's not that only one particular technique will give us all the informations, but rather we might need to make use of more than one or a combination of different techniques, and that will give us a more complete systematic overview of the system. Okay, so with that I would like to finish here, and thank you all for your time. Hello. Hello.
Yes, sir.
Am I audible?
Yeah. You are audible, sir. Thank you, sir. Thank you. So this session is now open for question answers. So if participants have any questions, you may unmute yourself. You can ask, or you can put the questions into the chat box. I will read it for the sir. Participants, if you have any question, you can directly ask to the Dr. Ray, or you can put the question onto the chat box. So as I can see, few questions are there. So, sir, Soumya Jyoti sir, I'm just trying to read out the question. Huh? It's okay for you?
No. Yes, please.
Okay. So Jyoti Pandey is asking, sir, how can we decide the aspect ratio in AFN imaging?
Okay, so aspect ratio in the sense you are saying of the image. Is it about the image? Okay, so see, that is something which is kind of depending on how much area of sample you have scanned. Let's say if you measure it on a square area, or if you have measured it on a kind of, let's say, like slightly rectangular area. So depending on the area, or let's say the volume of the sample that you measure, that will determine. But you are, I mean, if you are talking about like this 3D, this texture, so like what I have shown, that is kind of something which is up to you. Like it's not something which is, let's say, I mean, it's basically like your mom, I mean, computer controlled. Okay, so you have the height information, and you can plot it either through a color plot, or you can do a line scan also, whatever you want. Is it clear? Okay, so that is not like something which is related to the experiment.
Okay, so I
This is like a display, how you are going
so
to
I
display the
think
result.
it is okay for Jyoti Pandey. So Pankrishna sir is asking for please share the PPT. So as
Okay, I'll
yeah,
share. Yes,
then
yes.
we will share it in the group. Then I can see, can liquid sample be done in AFM?
Yes, liquid samples can be done, but this is not typically like any, how can you say, like a solution cannot be directly done, but rather if you have a liquid film, or let's say a slightly softer liquid surface, then which is kind of present on a solid surface, then that can be measured.
Yes.
So for example, like, you know, like this Langmuir broad jet film people do deposit, and so that can, like, membranes can be measured, and also liquid films can be measured.
Yes, exactly. So next, as I can see, how can we prepare sample for PNR technique?
Okay, very good question. Okay, so as you see that this is a reflectivity experiment. So here what you need to do, you need to have a thin film sample. Okay, which means that typically you have to have a substrate of area depending on, let's say, either 1 by 1 centimeter or slightly more, let's say 1 inch by 1 inch. So if you are having powder, somehow you have to get a thin film out of it. So there are several ways. For example, let's say if it's an oxide material, so I mean, just for simplicity I am taking, then what you can do is that from that powder you can get a pellet. Okay, so kind of like you heat it, and then you put it in a furnace, and then you sinter it, and then kind of you create a pellet. And with that pellet you can do something like a pulse laser deposition on a substrate. Now then you will get a thin film. That thin film you can take it, and you can do the neutron reflectivity measurement.
I think that clears the doubt. So next, as I can see, Dr. Ashok Kumar is asking, can we do cross-sectional view of the multiple layers of the sample using AFM?
Okay, very good question. So depends on basically what you are trying to look at. So for example, let's say sometimes what people do is that, like suppose I have multiple layers of a thin film. Okay, and I want to see what are the thicknesses of individual layers with the FM. Then what I can do is that, let's say I have 3 layers. So what I can do is that I can, after the deposition of the first layer, I cover a part of the sample, and then I grow the second layer. Okay, then I cover another part of the sample, and then I grow the third layer. So that way what happens is that I have some part of the sample where I have only 1 layer, some part of the sample where I have only 2 layers, and some part where I have only 3 layers. Now if I do a scan along different directions, then I can get a step like feature. Okay, so because let's say if I am at a area of the sample where I have 3 layers, so the height will be quite high, I mean thickness, or let's say the height will be large, right? From there, if I'm going to the part where I have only 2 areas, then there will be a big jump, right? So then I can basically take that jump to or I can use that jump or the height to know the thickness of this third layer. Similarly, if I go from second to the first layer, like in another direction, so that way I can also get the height information of this second layer. Okay, so that is okay, but so that is one way you can do this thing. but a cross-sectional view. Okay, so I mean, yeah. So cross-sectional in that sense, like yes. So I mean, I believe that that is something which is kind of like let's say cross-section kind of thing. But if you want to mean that, if I have to kind of cut the sample and like vertically I have to measure, then I believe it's a little tricky job, difficult job. I will not say it's impossible, but it's a difficult job. Okay, it might be possible.
Okay.
Okay, yes, yes.
So as I can see, there are few more questions. Is contact mode more preferable for liquid samples or non-contact?
Okay, very good question. So basically, it depends. Okay, so it's usually preferable. Contact is more. I mean, it depends on like how the liquid surface is, but it is kind of more preferable.
Okay. So Alok Das has one more question. Sir, can you please suggest a good software for AFM image analysis?
Good question. I don't have an exact name now, but you can use basically any image analysis software. Even you can use MATLAB also. Okay, if you want, or you can use like any graphics, like kind of like basically you will have a 2D image and you just get the kind of this. Let's say 256 by 256. This vector information will be there. So any image processing software you can use. Anything. I mean MATLAB I can say basically. Okay. So I don't know the exact recent names, because what happens these days is that most companies, they come up with their own software, and that kind of like, I mean, this kind of goes with that. So
Yeah.
MATLAB is something which you can use, of course, but I think nowadays people are using Origin also.
So I think all the questions are answered. And even if participants have any more questions, you can directly mail to Dr. Ray. I think he will be happy to answer your all queries. With this note, I think no more questions are there. Oh, I think one more question is there. Yes. Dr. Uddin is saying, sir, would you be pleased to say something about the preparation of biological samples for SAM analysis?
Good question. Actually, I unfortunately I am not like very much experienced with this, because I don't work with biological samples. So no, sorry, unfortunately I can't comment on this now.
Okay, okay.
Okay, okay.
So, okay, sir. Okay, sir. So it was a wonderful talk, I must say. And all our participants are saying it was a very nice lecture and to share PPT. Once you share us, then we'll share the PPT to all the participants.
Yes, yes, yes. I'll share it with you, and then probably you can then share it back.
Yeah, yeah. You just share to Dr. Hussain and
Okay,
Professor
okay,
Hussain, and he will share it.
okay, okay. No problem. Okay, okay. I'll do that.
So here we are winding up this session for this evening, and hope participants enjoyed this the fourth evening of the ATAL FDP program. So tomorrow again we have the fifth day program. Tomorrow the lecturer will be Professor P.K. Pal from Jadavpur University. So I must invite all the participants to kindly join the session as per schedule. Professor P.K. Pal will be giving lecture on fluorescence spectroscopic and electrical characterization of organized molecular assemblies on solid substrate. With this note, I am winding up the session on behalf of Department of Physics, Tripura University. Thank you. Good night.
Bye.
Bye, sir.